Well, we're going to work with two new types of functions. Inverse functions are just an extension of something that we've already done in evaluating functions and understanding function notation. Composite functions might be a new idea. Nonetheless, it's not too complex. It's just a new idea to present. There are two things that we want to accomplish here today. First one, a composite function is a function that's made up of smaller functions. The other thing we're going to do is, given a function, we're going to find its inverse. Almost all functions have inverse functions. I'm going to show you how to find those and what exactly they do. So we're going to start with that first one. We're going to start out with composite functions. First of all, you can take a function and plug more than just numbers into it. You could plug in other variables or even other functions. You could plug in symbols if you wanted to, but we're not limited to just plugging in numbers into functions. I'll show you an example of that here. For example, f of x is equal to 4x plus 7. That's a nice simple function to start out with. We want to find f of 3a. Well, anything that gets popped into this parentheses is essentially what we're going to plug into the function. So, for example, if you wanted to, you could say f of smiley face is equal to 4 times smiley face plus 7. That would be true. Now, smiley face usually doesn't have a lot of mathematical implications, but you can see we can put anything in that spot and we can evaluate it at the function. I promise you that will not be a quiz question or a test question for that matter. But what we can say is suppose we want to evaluate f of 3a. Well, then we're just going to plug 3a into that function, and that becomes 4 times. The x comes out, the 3a goes in. And so f of 3a becomes 4 times 3a is 12a plus 7. We're done. 3a is itself a function, you might say, and we plugged it into the function f and we created a new function. Let's do one more example that's a little bit more involved. Suppose we've got f of x is equal to 2x squared over 4 plus 3x. We want to find f of 2n plus 6. Well, what we're going to do is we're going to fill in 2n plus 6 into every place where x occurs in that function and simplify it. So this will become 2 times 2n plus 6 squared over 4 plus 3 times 2n plus 6. Everybody agree with that? Now we just need to simplify that mess. So let's simplify. 2n plus 6 squared, that's the first thing we need to do by our order of operations. So we need to take 2n plus 6 and square that out. That's going to become 2 times what? 2n plus 6 squared. That's going to be 2 times 2n plus 6 times 2n plus 6 over 4 plus 3 times 2n plus 6. All right, well, we need to FOIL this out. So this becomes 2 times. First terms give us 4n squared. Outside terms give us 12n. Inside terms also give us 12n, so I'm going to combine those two in one, plus 24n. And the last terms give us 36 all over 4. Okay. Bring that back up here. Now we can simplify that just a little bit. We'll distribute the 2 into the parentheses, and we have 8n squared plus 48n plus 72 and we'll distribute this 3 into the parentheses at the end. That's 6n plus 18. All right, look good so far? All right, now we can do some canceling here. All these coefficients that are all over 4 are all divisible by 4, and so we can cancel this off. That 4 will cancel with the 8, and it becomes a 2. With the 48, and it becomes a 12. And with the 72, and it becomes an 18. So this is equal to 2n squared plus 12n plus 18 plus 6n plus 18. And at that point, we're ready to combine like terms, and we'll have our result. Combine our like terms, we can conclude that f of, thank you, 2n plus 6 equals 2n squared plus 18n plus 36. And there it is. Okay? Substitute it in, simplify. That's basically the idea we need to follow for evaluating all these types of functions. Now, what we've done, we haven't addressed it yet, but what we've done is we created a composite function. The function we evaluated was f. The function we plugged into it was 2n plus 6. Now, this could have just as easily had its own name. We just called it 2n plus 6, but it could have had a name like g or k or anything other than f, which is already used. Well, that's what a composite function is. We've done it. Now, let's just kind of formally state that. If you take one function and plug it into another one, you made a composite function. You created a composite function. And if you think about the word composite, what does the word composite mean? There's composite materials combined, or a collection of different things. That's what a composite really is. It's made up of several things. Composite function, if we have a composite function where we take some function, we'll call it g of x, and plug it into f of x, that's how we write it. We say we plug g of x into the function f of x, and we say that the function is f of g of x. Okay, we want to find, oh, I didn't tell you what we want to find yet, but we want to find f of g of x. So which function are we plugging into which? Which one are we going to take and stuff in? We're going to stuff g into f. Okay? So what this means is f of g of x, you'll see this two ways. Your book uses brackets out here. It's also absolutely acceptable, and you might find this handy, to just use parentheses, a second set of parentheses. So we're taking g of x and plugging it into f. This is the same as saying we want to find f of. Now, instead of calling the name g of x in there, we can put the function. G of x is 4x minus 9. Does that make sense? Instead of referring to it by name, we're referring to it by what the function actually is. Basically doing a substitution. F of 4x minus 9. Well, what is f of 4x minus 9? That's equal to (4x minus 9) squared plus 16. Now that is our composite function. We just need to simplify it. 4x minus 9 times 4x minus 9 plus 16, which is 16x squared minus 36x minus 36x, that's minus 72x, plus 81 plus 16. And so then we can conclude that our composite function equals 16x squared minus 72x plus 97. And we're done. That's the new function we formed by plugging one into another. Same two functions. This time, instead of finding f of g of x, we're going to find g of f of x. Okay. Now, let's evaluate g of f of x. Now, this time, we're going to take the function g, and we're going to evaluate it at what? X squared plus 16. That is f of x. We're saying plug f into the g function. So we're going to take x squared plus 16, and we're going to plug that into the g function. What does the g function tell us to do with our input? You got it. Exactly. G function says you take your input, you multiply it by 4, and you subtract 9 from it. So g of x squared plus 16 is going to be 4 times x squared plus 16 and subtract 9. Now we just need to simplify that. We took x and plugged it into g, and now we're going to simplify it. So we get, this one's easier to simplify, 4x squared plus 64 minus 9. So g of f of x is equal to 4x squared plus 55. And that one's done. G of f of x. So in general, are f of g of x and g of f of x equal? That is to say, does it matter, or will you get different results whether you plug g into f or f into g? Absolutely. Yes, it does matter. All right? Now let's answer the second part of this question. We want to find, now you're going to love this. All right? Hold on to your socks. You're going to like this. We want to find g of f of negative 5. You have two options for this. What should we do if we want to find g of f of negative 5? We're just going to take negative 5 and plug it in where? G of f of x. Okay? Well, that's good news. We can just go down here and say that, yeah, we better go up here. I'm going to rewrite this up here just to get a little bit more room. We know now that g of f of x turned out to be 4x squared plus 55. Okay? We want to find g of f of negative 5. Well, we're just going to plug negative 5, plug it into this function. This is still its own function. It just has kind of a tricky name. Its name is g of f. All right? Well, this turns out to be 4 times negative 5 squared plus 55. So what does this turn out to be? Well, let's save some room and put it up here. 4 times negative 5 squared plus 55 is 155. Okay, but now this is the part I told you there was something exciting coming up here, and here it is. You don't have to evaluate g of f of negative 5 that way. You could do this. What is f of negative 5? Well, just go up here. What is f of negative 5? Yep. F of negative 5 was equal to negative 5 squared plus 16. That's 41. Okay? Well, what is f of negative 5? We just said that's 41. So finding g of f of negative 5 is really the same as finding g of 41. We took f of negative 5 and we found out what that is. So we plug in, what is g of 41? G of 41 is equal to 4 times 41 minus 9. Whoops. 4 times 41 minus 9, and what is 4 times 41 minus 9? 155. So we could plug negative 5 into the function g of f, or we can figure out what f of negative 5 is on its own and plug that into the g function. We get the same thing either way. Okay, they do the same thing. I'll let you catch your breath for that for a minute, and then we're going to do a couple more examples here. Inverse. Now we're going to work with inverse functions. Now you know what a composite function is. Think about this for a minute, okay? For the operation of multiplication, almost every number has got something called a reciprocal, so that when you multiply the number by its inverse or reciprocal, you always get 1. So there's a couple examples. If we take the number 7, multiply it by its reciprocal of 1/7, you get 1. If you take a over b, multiply it by its reciprocal, b over a, you get ab over ab, or 1. Every operation, I shouldn't say it quite that way, but the operation of multiplication has something called an identity. The multiplicative identity, the magic number for multiplication, you might say, is 1. What makes it the identity is you can take 1 and multiply it by anything, and what do you always get? Same number. 1 times 10 is 10. 1 times 15 is 15. 1 times x is x. When you take multiplication, the operation of multiplication, and apply it to the number 1, it doesn't change whatever you're starting with. Make sense? Okay. Well, what that means is that every number, when you're dealing with multiplication, must have some inverse that'll get you to the identity. And it's called the reciprocal. Now, addition has the same property, but its magic number isn't 1. What number do you use with addition that doesn't change your original number? 0, exactly. And that's the other example I'm going to give you. For the operation of addition, the identity is 0. You can take any number and add 0, and you're stuck with your same number. 0 doesn't do anything when you use it with addition, just like 1 doesn't do anything when you use it with multiplication. And every number has an inverse. For addition, though, we don't take the reciprocal, we change the sign. So 8's inverse when dealing with addition is negative 8. And when you add those two, a number and its inverse together, you get 0. If we have some other number, negative n, the inverse is always just going to be the same value, different sign, which in this case would be n, and you end up with 0. Well, that's the idea of an inverse. An inverse will always get you back to the identity. Most functions also have an inverse function that will get you back to the identity function. Not all functions have an inverse, but most do. The notation we use for an inverse of a function f of x is a little exponent of negative 1. Well, the identity value for functions is x. What can we do to a function so that it'll always get brought back to x? That's the question we want to answer. Now we're going to see how that works in a minute, but the first thing you need to know is, okay, if you've got a function, how do you find the identity? Well, when we're talking about multiplication, we take the reciprocal. When we're talking about addition, we change the sign. But how do we find the inverse of a function? All you do is write the equation out, write the function out, switch x and y around, and then resolve it for y. That'll tell you the identity. So let's do an example. Let's suppose our function is 5x minus 12. f of x equals 5x minus 12. Okay, well, the first thing you do is you rewrite this, get rid of the name f, and put in y. That makes life easier. Remember, this is always just taking the place of y. It's just giving it a name. So f of x equals 5x minus 12 is really just saying y equals 5x minus 12. Now we're going to switch x and y. So instead of saying y equals 5x minus 12, we say x equals 5y minus 12. X equals 5y minus 12. And now we're going to solve for y. When we're done, we've got the inverse. So let's take this and solve it for y. We know that x equals 5y minus 12. Solve it for y, let's add 12 to both sides. X plus 12 equals 5y. We're almost there. Divide by 5. And we end up with x plus 12 over 5 equals y. Well, you're done. Now you just go back and rename it. When we switch this, we got y equals x plus y over 12, so we can conclude then that the inverse of x equals x plus 12 over 5. Now, here's what I'd like you to do. I would like you to, little math game. I want you to think of a number between 1 and 10. Okay, just think of a number. Prepare to be amazed. I want you to take your number and plug it into the function f. Okay? Probably be able to do that in your head without too much trouble if you picked a low number. Take your number and plug it into the function f. Multiply it by 5, subtract 12. Got your answer? Okay? Jot that down. Jot down your number that you got right now. Okay, now you haven't forgotten what number you started with, have you? Okay. Now take the number that you just got, the number that f yielded, the one you just jotted down, go down here and plug it into the inverse function. What do you get when you evaluate the inverse? Your original number. That's what the inverse function does. Okay? I'll let you catch your breath. Again, that's pretty amazing. Okay, so that's what the inverse function does. It takes your input value. This assigns an output to your input. The inverse puts you back home. All right? It sends you back to your original value. Now, to draw you a picture of kind of what that is doing in relation to what we were talking about on Tuesday, remember what a function does is it takes some number from your input value and assigns it to some number on your output value. We call that process f of x. That function is a switching from this group to this group. I'm just going to pick on one person. Kyle, what was your number that you picked to start with?
8.
Good. Okay, you pick 8. You plug in 8, you get 40 minus 12, 28, right? Then when you plug 28 back into here, you get 40 over 5. It puts you right back there. That's what the inverse function does. It sends you back home. This is a new example. It looks almost exactly the same, but note, I'm starting out with the same function here. F of x is equal to 5x minus 12. We want to find f of f inverse. Well, what we just established was, we started with that, and in the previous example, we showed that f inverse of x is equal to, let's see, it was x plus 12 over 5, wasn't it? Okay. Now, what we want to do is we want to find the composite function that you get when you plug an inverse into the original function. Maybe you can guess what you're going to get. Okay, so we want to find f of f inverse. That means we want to take f and plug in that. Everybody agree with that statement? We want to find f of f inverse, a composite function. So that means we want to take the inverse function and plug it into the function f. And that's what we're doing. So we want to find out what f is when you plug the inverse into it. Well, what do you do with the f function? The f function says you should take your input, multiply it by 5, subtract 12. So we're going to take 5 times x plus 12 over 5 and subtract 12. Well, what does that equal? 5's cancel, right? So you're left with x plus 12 minus 12, which is x. In other words, if you plug a number into an inverse and then into the original function, that's what I just had you do with the number in your head, what do you end up with? The original number. X is the identity for composite functions. If you take a composite function with a function in its inverse, in this case you ended up with x, this statement right here, not very interesting because it is always true. If you plug an inverse into the function itself, you always end up with just x. In other words, plug a number into the inverse and then into the original function, you will always end up with the original number. That's why you could all do it and you all ended up with your original number. It doesn't matter. Okay, well let's take a look at one more here before we need to leave. There's our function g of x. This is a new one. We want to find out what the inverse is. Okay, what's the first thing you do to find the inverse? Rename this as y. We rename it and call it y equals negative 3/4 x plus 2. Again, that's really just to make all this writing faster. Y equals negative 3/4 x plus 2. Good. Now what do? Switch them. Got to switch. So this becomes x equals negative 3/4 y plus 2. Now we want to solve that for y. What do you want to do? You could, or if you don't like the fractions, let's get rid of all those. Let's multiply everything by 4. So if we do that, we get 4x equals 4 times negative 3/4 y plus 2. Multiplying everything by 4, so we get 4x equals negative 3y plus 8. So subtract 8 from both sides. 4x minus 8 equals 3y. And then we can conclude that y is equal to 4x minus 8 over 3. Oh, thanks. I lost a negative sign there, didn't I? Good. Negative 3y, so then we're going to divide everything by negative 3. And then we can make a conclusion here. The inverse of g this time is equal to, now 4x minus 8 over negative 3 is really the same as, if we change all these signs, we want to make that positive, 8 minus 4x over 3. And we found it. There's the inverse function. 8 minus 4x over 3 is the inverse of g. Yep. Now the last question today, put your pencils down, because the last question I'm going to ask you don't need your pencil to answer. The last question is, find g of g inverse of x. Thank you. It's x. g of g inverse of x means if you take x and plug it into the inverse and then back into g, you end up with x. No work to do. We could prove it. We could do that. We could plug this into there, do all the algebra, but it'll work every time. We saw it once. It's always true. Always.